Hello, human geographers, and welcome back so that we may continue our discussion about maps. Last lecture, we talked about the basics of maps and how thematic maps tell a story. Now, we're going to get into the different types of stories that they tell and how they can influence our understanding of the information behind that story. There are 5 types of thematic maps. Those are choropleth or categorical maps, dot distribution maps, graduated symbol maps, also known as proportional symbol maps, isoline maps, and cartograms. Now, we're going to go ahead and take a look at each one of those in greater depth. We'll start with choropleth maps, which are the most common type of map that you've probably seen before and will certainly see going forward. Choropleth maps typically have different shades of one color to represent variation in different amounts of a single data set. For example, you see different shades of green used to illustrate a world map looking at physiological density, that is, the amount of people per kilometer of farmland. And usually 4 to 5 shades, 4 to 5 classes is the ideal. If we have less than that, then we're starting to group together data that we should differentiate between. And more shades or classes than that can obscure our ability to differentiate between those classes of data. Categorical maps represent different kinds of data and thus usually have different colors. In this case, we see several different classes of climate with variations within each one. And these maps tend to be very common, and thus people usually have experience reading them. However, they can be very general, and that can cause issues with the way that the data is grouped together or visualized. So let's dive into the weeds a little bit as far as grouping or classifying of data goes. All 4 of these maps show the same place, Colorado, at the same scale, county scale, and it shows the exact same data. This data is persons per square mile, or what we'll define in this class as arithmetic density. The first grouping of data is equal interval. That means there is a constant interval between classes. In this case, that interval is 1,053.07 people per square mile. They took the highest number and the lowest number, subtracted them, then divided into 4 equal intervals of basically 1,053. It doesn't matter that every county in Colorado is in the lowest class except Denver County. Every class has equal intervals, equal spaces. The next grouping is called quantiles, or equal frequency. This means that the 64 counties of Colorado are divided up into 4 equal groupings, regardless of the interval that this class may contain. So notice that the lowest class ranges from 0.42 people per square mile to 2.84, and that's a rather small interval for the 16 smallest counties. But then notice the highest class, which ranges from 19 people per square mile to 4,212. That's a huge interval for a group of 16 counties. Our next way of grouping data is using standard deviation, which is a mathematical way to divide our 64 counties of Colorado into 4 classes based on their average number of people per square mile. So in Colorado, the average is 637.01 people per square mile. And the standard deviation from that average is 531.64. So both of the middle classes are exactly 1 standard deviation from that average. And then the other 2 classes encompass the rest of the counties out to the extremes, both high and low. Our final way to group data is into different classes that we call natural breaks. This method tries to find a balance between the number per class, what we call frequency, and the gaps between classes, we call those intervals. It tries to find the sweet spot in the data where breaks are natural. So this slide got really technical really fast. And last lecture we said an important question is, so what? So what is the so what of this slide? Why is it important? Let's use a hypothetical example. Let's say that you live in Colorado and you write an article arguing that Denver is too crowded and that people should leave or the government should do something to fix it. Which map would you use? What if you wanted to argue the exact opposite, that Denver is not overcrowded and is very similar to other counties? Which map? What if you wanted to argue that the math is on your side, that math supports your map? What would you choose? And what if you wanted to argue that you can provide some kind of compromise between these conflicting points of view? Now, are any of the arguments flat out wrong? Are any of the arguments lying? Remember, all of these maps are made with the exact same data. So cartographers have the ability to change the message of a map without lying, but by making a simple choice. So we have to be critical of just about every map that we see and try and decipher the story the cartographer is trying to tell. And that can be challenging. Dot distribution maps, as the name implies, will show how things are distributed. And this can be really helpful in doing geographic analysis. But it also can be really difficult to collect this data. All of the dots have to be fixed to a specific point, what we call point data. They cannot just be thrown randomly on the map. So tools like GPS are often used to help collect and map this type of data. Now, dot distribution maps are often confused with another type of map that we're going to look at next. So let's go ahead and give a few clues to help differentiate them. It is not uncommon for dot distribution maps to have no key. Notice the map on the right, which displays the location of Walmarts throughout the United States. There's no key, there's just dots. And those dots show the location of each Walmart over time. The second map does have a key, but that's because we have combined a dot distribution map with a categorical map. The key is for the categorical map. So we can see both the distribution, that's the dots, as well as the racial or ethnic groups behind the categorical map. In addition, notice on both maps, the dots do not change size. And that's important because on proportional symbol maps, particularly graduated circle maps, the dots do change size. And notice that on both maps, there is a key. So we can tell what the different sized symbols actually mean. Proportional symbol maps are nice because they combine a graph and a map together. We can see location, but we can also see change as represented in the proportional size of the symbol. Now, these symbols are often circles, as you can see on the graduated circle map, but on flow vector maps, we often see arrows of different sizes, so we can determine movement as well as proportional change. But symbols can really be anything you want, as long as those symbols change in size relative to the data they're displaying. Isoline maps are probably our least common type of map, but that doesn't mean that they can't tell an important story. They're called isoline maps because the lines connect points of equal value. That's what the prefix iso means, equal. So If you take a look at the 5 maps of the US, they connect points of time based on how far a person could travel in hours, days, weeks, etc., depending on the time and mode of transportation. So in 1800, it could take you weeks to get from New York City to Michigan. But by 1930, it would take a matter of hours. And isoline maps can be a little difficult to read if you haven't had much experience with them. So notice that lines that are close together have steep or rapid change, whereas lines that are farther apart have more gradual change. Take the map at the bottom. This is an elevation map, which is perhaps the most common type of isoline map. Lines that are close together represent rapid elevation change, meaning that those areas are very steep. Then you have areas where the lines are further apart, which are more gradual inclines and would perhaps be less strenuous for someone hiking up a hill or a mountain. This is an interesting take by one of the approved human geography textbooks. They applied all 4 types of maps to the same data set, specifically population density by county in California in 2010. Let's see if you can remember what they were all called. And this is something I often do in my class. You'll hear me ask, what type of map is this? So let's practice. What type of map is this? What about this? And this one? What type of map is this? Now, one additional clue about dot distribution maps and graduated circle maps, the 2 that you see up at the top, notice that the dots have to be in a specific location because they use point data. They can't tell their story well without it. But in the graduated circle map, the dots are fixed in the center of the county. They don't use point data. All of these maps use the same data. But do you think they tell the story of population density in the same way or in slightly different ways? How do you think a passive, non-critical viewer of this data might be confused or misled by a particular map? Our last type of thematic map are cartograms. Cartograms are kind of fun. In much the same way that proportional symbol maps combine a map and a graph, so do cartograms. But now, the map is the graph. Cartograms distort the land area relative to the data that it represents. So on the left, we have a cartogram of global population. Notice China and India, which look like they've been inflated by a pump, representative of their massive populations. Then you notice Canada, which looks like it was left out in the sun to shrivel up. Now, while these are fun maps, they are subject to ambiguity and oversimplification. The wretched dollar on the right shows populations that are living on less than $1 a day, which is a marker for extreme global poverty. China and India lead the pack. Why do you think that might be? Do you think that since they have over a quarter of the world's people, they might have a lot of the world's poorest people? For China and India, does this map tell the story of their population or of their poverty? And that's important for us to understand. This is just one more example of how we must be critical of these maps and look beyond the map to what the real story is. A few more quick things that we need to introduce before we move on. Maps can be interrupted or uninterrupted. We discussed this briefly last lecture, but these choices are ones that cartographers can make for a variety of reasons, depending on the story that they want to tell. Maps can also be rotated. This map has been rotated 180 degrees, but if you look closely, the lettering is written such that you can still read it even though the orientation has changed. The choice to put the northern hemisphere on the top of a map and the southern hemisphere on the bottom is just that. It's a choice. And so when we're speaking about maps, we want to avoid descriptors like up or down because those terms are relative to the orientation of the map. We should instead focus on terms like north or south because even though we've rotated this map, has the southern hemisphere changed? Same goes for centering. Maps can be centered on different locations. It affects our perspective of the world in much the same way that rotating the map might. We may feel closer or farther from an area depending on the choice the cartographer makes. And these choices are again made for a variety of reasons. Both of these maps are the same projection, that is the Winkel triple, but one is centered on the Pacific Ocean and the other is our more common Atlantic-centered map. And I say our more common map because if you grew up in Asia, you'd have spent a lot more time looking at the map on the left that's centered on the Pacific Ocean. Now, throughout the year, I will periodically drop in additional articles for those students who might be interested in getting some extra perspectives. This article asks the question, do maps create or represent reality? It's an interesting read, and I think that those of you who choose to read it will find it generates some new ideas and maybe some new questions. Shifting gears, now we're going to be talking about a specific aspect of cartography, and that is scale. Here's the definition. The representation of a real-world phenomenon at a certain level of reduction or generalization. Generally, it is the relationship between the portion of Earth being studied and the Earth as a whole. So what are those key words and phrases in this definition? And this definition introduces to us the idea that there are different types of scale. This idea is certainly one of the more challenging aspects for students, but it is a vitally important one for us to understand in both our understanding of the material that we're going to cover and our understanding of the world, as well as for the AP exam. As we just mentioned, there are different types of scale, and depending on which textbook you read, there are either 2 or 3 types of scale. And what I've done here is tried to show the way that these concepts are combined or discussed. On the left, we have map or cartographic scale. This is the most challenging of the bunch and the one that we're probably the least familiar with. Cartographic scale is the degree to which something has been reduced on a map compared to the same space or feature on the Earth. And there are 3 types: a word or written statement, representative fraction, abbreviated RF, and a graphic or visual scale. On the other side, we have observational or methodological scale. And then there's 2 categories within that. And I'm going to go a little out of order for a second. Let's jump to the bottom. Phenomenon scale is the scale we use to describe at what level something is happening. Perhaps the best example is something that we're quite familiar with. COVID-19 is a global pandemic. That's a phenomenon scale. It's happening globally. And so you might have used or heard large scale and small scale used to be synonymous with global and local. But today we're going to explain why that's going to change a little bit for us. And finally, scale of analysis is perhaps the most important scale that we're going to be using throughout the year. In much the same way that I will ask you what type of map something is, I will almost always be asking, at what scale are we analyzing this? This refers to the scale at which the data is grouped together. Are we looking at census tract data? Are we looking at county data? National data? It'll take a little bit of practice, but it's important. So we talked about cartographic scale as the degree to which something has been reduced on a map compared to the same space or feature on the Earth. And there's three ways of depicting that level of reduction. One is a written or word statement. In the example here, 1 inch on the map represents 10 miles on the surface of the Earth. A graphic or visual scale is a visual representation of space. So this amount of space on the map represents 10 miles on the surface of the Earth. And probably the most challenging of these three is the representative fraction. And you can probably guess which one has shown up on the AP exam the most. Yeah, it's representative fractions. So we're going to spend a little bit more time on this one, but don't worry, you're not going to have to do any math. But there are a few things that we want to remember. When we talk about RF scale, or representative fractions, the number in the numerator is the same unit as the number in the denominator. So in the example on the screen, 1 unit on the map equals 633,600 of the same unit on the Earth's surface. And what's kind of cool is that it doesn't matter what unit we use. 1 inch on the map equals 633,600 inches on the Earth. 1 meter on the map equals 633,600 meters on the Earth. But remember, you can't change the units. Now notice in the word statement, you can change units. 1 inch equals 10 miles. But for RF, representative fractions, that's a no-no. Now, to go into this further, and please, if you get a little lost, don't worry. Rewind the video, watch this section a couple times. Please bring those questions to class as well. With cartographic scale, we use the terms large scale and small scale to refer to the level of detail that is visible on the map. So a large scale map is one that is a very small area that provides lots of detail. Large scale, lots of detail. But maybe now you're thinking, wait, I thought large scale was supposed to be something that was happening over a large area. Remember, that's phenomenon scale. And we'll use terms like global for things like that. Right now, we're talking details on a map. Large scale, lots of detail. So from here on out, large scale and small scale will be used exclusively for cartographic scale. All right? We want to avoid some of that confusion. If we need to talk about something happening around the world, we'll say it's happening at a global scale. Or if it's in one location, it's happening locally. Hopefully that'll reduce some of that confusion. But back to RF. We can decipher the level of detail by looking at the denominator of the fraction. The bigger the number, the bigger the area that is depicted, which means that it is a smaller scale because it's providing less detail. Let's see if we can come up with an easy way to remember this. And I promise this has shown up on several multiple choice questions, so it's definitely a topic that they like to ask. My method for remembering this, you've already heard me say it a couple times. Large scale, lots of detail. Large scale, lots of detail. Kinds of rhymes. All right? If I remember that, I can fill in the rest of my flow chart and answer just about any question that deals with cartographic scale. Large scale means there's lots of detail. It has lots of detail. It must be a small area because it's providing lots of detail. A smaller area is going to mean a smaller number in a representative fraction. And now is when it comes full circle. If it's a smaller number, it's a larger fraction. Larger fraction, larger scale. You think of pizza, for example. One pizza has 4 slices and one has 12 slices. The smaller number, 4, has a larger fraction of the whole. Larger fraction, larger scale. And it doesn't matter the way that you remember this. Maybe math is like a second language to you and you just need to remember large scale, large fraction. You can work the rest of it out to get to the same answer. That's awesome, as long as you can work through this. And you must always have something to compare it to. If I were to show you this picture, this aerial photograph of downtown Seattle, and ask, is it large scale or small scale? The answer is, it depends. It's a smaller scale representation, showing less detail, than if you were looking at Pike's Place Market, if you were checking out the original Starbucks, if you were visiting the Seattle Art Museum, or making your contribution to Seattle's gum wall. It's just as awesome and disgusting as it sounds. But when you compare it to the greater Washington state area, a larger area, our original aerial photograph is a much larger scale representation of the Earth, showing more detail in a smaller area. You have to have something to compare it to. Now this slide is a nice review. At the top, you have phenomenon scale, ranging from global down to local. Where's it happening? On the next line, you have scale of analysis. How are we grouping that data together? And let's look at that for a second. You can actually add some additional scales of analysis. Below the census tract scale, on the far right-hand side, what it would be, we could add block groups, which are an even smaller component part of each census tract that we can group data into. And then on the far left-hand side, above the national scale, we could aggregate data, we could group data into continental scale, meaning by continent, or supranational. Now, just to be clear, we didn't say supranational, we said supranational, meaning above the national scale. And you can actually see 2 examples of supranational organizations in our visual, the United Nations and the European Union. These are groups of countries, and we can group data at that scale too. And while we're looking at the image, notice that we see some representative fractions on the right. As the area gets smaller, so does the representative fraction. And how does a cartographer decide what scale to use? It depends on the story that they're telling. Let's use a hypothetical example. Let's say that you work for a national retail chain and you're trying to decide where to build a new store. Data at the national scale won't really be helpful. Instead, if you zoomed in to the zip code scale, that might give us an idea where we should build our new store. We can find areas with potential customers who aren't having their needs met. It just depends on the story. So let's look at some real life material. We can start by asking a couple of questions. What type of map are we looking at? Right, this is a choropleth map. And the story that this map tells is about migration, particularly net migration. So the countries that are purple have net out migration, meaning more people are leaving. And the countries that are red have net in migration, meaning that they have more people coming in than leaving. So let's talk about scale. The scale of analysis, meaning the scale at which the data is aggregated or grouped, is the national scale. And we look at migration statistics for individual countries. That's the scale of analysis. The phenomenon scale is global because we're looking at a pattern that is happening throughout the world. Finally, the cartographic scale is small scale. We're looking at a large area with less detail. For example, the US has high net in migration, but where are they going? This map doesn't tell that story. But this map does. Again, let's start with some practice. What type of map is this? Again, it's a choropleth map. Good. This map is at the subnational scale, and we use that term for units within a country. In the United States, we call our subnational units states, but in other countries, they're called provinces, prefectures, territories, or cantons, or several other terms depending on what country we're talking about. Now, we get a better idea of where international migrants go when they come to the United States. For example, more people go to California than come to Nevada. But let's talk about Nevada and California for a second. Does every part of Nevada receive less migrants than every part of California? Let's change the scale. We can see that certain counties of California actually have net out-migration, while certain counties in Nevada have higher net in-migration than areas in California. Really, the biggest point that I want to stress at the end of this lecture is this. Whenever you get a thematic map, particularly a choropleth map, but really any map that tells a story, we should ask, what would happen if we changed the scale? If you zoomed in or zoomed out, how would that story change? What isn't told at the scale that you're currently at? Go back to that first migration map. That map doesn't tell us where people are going in the United States. Even this map doesn't show us where people are going in, say, Clark County. People are leaving Detroit, but where are they going? We have to be critical thinkers. We have to be critical consumers of materials, of maps. We have to ask questions. Anytime you see a map, start questioning it. And that's where we'll stop for tonight. Have a good evening, everyone, and I'll see you back in class.